Good morning everyone. Today, I'll be presenting on the hit or miss transform, a morphological operation used to detect specific shapes or patterns in binary images. It's particularly useful for identifying precise structures like T, L, or cross shapes, making it a powerful tool in image analysis and pattern recognition. First, we'll start with an introduction to understand what the hit or miss transform is. Next, we'll look at the mathematical concepts and basic erosion that form its foundation. Then, we'll go through the algorithm and implementation to see how it works in Python. Finally, we'll discuss the results, applications, and summary to review what we've learned and where this transform can be applied. The hit or miss transform, HMT, is a fundamental operation in mathematical morphology used to find exact shape matches in binary images. It uses two small matrices called structuring elements, one to match the shape of the object we want to detect and another to define the background pattern around it. Only those pixels where both the shape and its background fit perfectly are detected. Hence, HMT is widely used for precise pattern recognition in images. Now let's look at the mathematical concept behind the hit or miss transform. It is represented as A*B equals A erosion B1 and A erosion B2. Here, A is our binary image, B1 represents the foreground structuring element, and B2 defines the background. The operation performs erosion on both the image and its complement, and then takes a logical AND of the two results. This ensures that only those pixels that match both the object and its background pattern are detected. Before understanding the hit or miss transform, we need to understand erosion, one of the basic morphological operations. Erosion works by shrinking the foreground objects in a binary image. When a structuring element, SE, moves over the image, a pixel remains one only if the SE completely fits within the foreground region at that position, otherwise, it becomes 0. This process removes small irregularities and isolates the essential parts of shapes, making it a key step in the hit or miss transform. Now let's look at the algorithm for the hit or miss transform step by step. 1. Input a binary image A2. Define two structuring elements B1 for the foreground and B2 for the background. 3. Perform erosion of A with B1. 4. Find the complement of A, as, and perform erosion with B2. 5. Intersect both results using a logical AND. The resulting output highlights only those pixels where the foreground and background patterns both match the structuring elements exactly. Let's discuss how we implement this algorithm in Python. We begin by importing the necessary libraries, NumPy for numerical and matrix operations, SciPy's ND image for performing morphological operations like erosion. Next, we define the binary image A, which contains multiple small shapes such as T, L, or plus. We then define two structuring elements. B1 for the foreground representing the pattern we want to detect, for example, a T shape. B2 for the background representing the surrounding pixels that should remain 0. This setup allows our algorithm to focus only on areas that exactly match both structures. This slide shows the output from the previous step, displaying the input binary image A along with the structuring elements B1 and B2. Here, B1 represents the foreground pattern we aim to detect, and B2 defines the surrounding background. Both are essential for performing the hit or miss transform. Once our image and structuring elements are defined, we perform the following operations step by step. 1. Erosion of image A using structuring element B1. Foreground erosion. This operation checks where the structuring element B1 fits exactly within the foreground ones of the image. The output highlights those regions of A that match the shape of B1 perfectly. This result helps in identifying the potential locations of the desired object, for example, the T-shaped region. 2. Complement of image A. Next, we compute the complement of the input image using the formula A_comp equals 1A. This step reverses the pixel values. Ones become zeros and zeros become ones, helping us focus on the background part of the image. 3. Erosion of the complement image using structuring element B2. Background erosion. The complement image A is then eroded with B2 to ensure the background pattern around the detected shape also matches. The resulting output highlights areas where B2 fits perfectly within the background, zeros, of the original image. At the end of this stage, we generate two key outputs: foreground erosion. Erosion of A with B1. Background erosion. Erosion of A with B2. These two erosion results are displayed in this slide to visualize how both the object and its background are separately analyzed before performing the final hit or miss operation in the next step. Now let's analyze the final output obtained from the hit or miss transform in detail. In the previous slide, we obtained two important erosion results, one representing the foreground, object structure, another representing the background, surrounding area. To combine these, we apply the hit or miss transform, defined as hit underscore or underscore miss equals eroded underscore a underscore b1 and eroded underscore ac underscore b2. Here's what happens in this step. 1. The hit or miss operation performs a logical and between the two erosion results. 2. Only those pixel positions that satisfy both conditions. The structuring element b1 fits perfectly in the object and the structuring element b2 fits perfectly in the background, are marked as 1 in the final output. 3. All other locations are set to 0, since they don't satisfy both conditions simultaneously. To identify the exact detected points, we use NP arg where hit underscore or underscore miss. Example output 2. These coordinates indicate the precise locations in the input image where the T-shaped structures are present. The hit or miss transform has a variety of real-world applications, such as 1. Shape detection identifying patterns like T, L, or plus in binary images. 2. Template matching, locating specific predefined shapes within an image. 3. Feature extraction detecting junctions, corners, and endpoints in structures. 4. Industrial inspection spotting defects or missing parts in manufactured products. 5. Medical imaging recognizing particular cells or anatomical features in scans. These applications demonstrate its importance in automation and computer vision. To summarize, the hit or miss transform, HMT, is a powerful tool in morphological image processing used to detect specific patterns in binary images. It relies on two structuring elements, one for the foreground and one for the background. By combining erosion and intersection, it precisely locates shapes that match both structures simultaneously. Through our Python implementation, we saw how it accurately identifies shape locations, making it an essential technique in pattern recognition and image analysis. Thank you for watching my presentation. I hope this explanation of the hit or miss transform helped you understand how mathematical morphology can be used for shape detection and image analysis. Please feel free to share your questions or feedback. Thank